when. So they made an hourly simulation. Every column in here is 1 hour of the year. So it's 8,760 columns, actually, one after the other, right? And this is anything that's colorful there is coming from renewables. And as you can guess, the light blue is all the electricity produced by wind. And the tiny yellow ones is all the electricity produced by photovoltaics, which is quite a bit less. The dark blue is water, red is geothermal, and green is biomass. Now what you can see is that sometimes columns reach very high. There's only little room left, actually. So what you can do now for every hour is you can subtract all the renewable production from the actual simulated demand. The demand is a bit higher here because what they calculated in is that we are going to use more electricity due to more electricity in the mobility sector that we foresee there in 10 years' time, right? More e-cars, right? So if you subtract all the renewable production from the actual demand, you end up with a graph that looks like this. Now, zero is, well, if the renewables were able to meet all the demand. Anything above zero is the residual demand, the residual load, what is still left over, not covered by anything yet. And then lines below zero are situations where there is more production, actually, than needed. So more electricity only from renewables. This is not yet counting in all the base load production from nuclear power plants, coal-fired power plants that we have in the country. Now, I put in a line there, the green line over there. This is the constant production of the base load power plants. It's about 37 gigawatts that we have at the net at the moment. It's getting a bit less now because we're switching off the nuclear power plants. So the actual zero line would be here. And then anything that is white underneath that green line is a surplus production. And anything that is still black above that green line is going to be not covered yet. And it's going, in 9 years' time, it's going to be a huge problem. We will have lots of situations where there's more energy than the system actually can take up. And still a number of hours where there's not enough. But, and here's the important thing in it, the problem only exists if we are not able to move these peaks. Move them to somewhere where we have more generation than at that moment we could actually take up. So what we need is basically flexible production and more flexible consumption. Because what you are all aware of is that electricity can't be stored in the system. We have to have this equilibrium at all times. And in Europe, the set point is 50 hertz. So we measure the frequency and have a look at the frequency. And yeah. Right.
There will be a balancing effect with neighboring countries running these big loads.
Right. Yeah. That is not taken into consideration here. And that is because at the interconnection points, actually, there is a certain amount of exchange possible, but it's limited. I'm not aware of what the limits actually is, but it's a couple of gigawatts, actually. So it's not possible to actually import all the amount that will be needed in this 2, 3, 4, 5, 6 hours, and then a couple of hours left after that, export anything that's in here. Importing, exporting to neighboring countries will certainly smooth out the situation a bit, but only a bit, unfortunately, unless we do not re-strengthen the grid and enlarge the interconnection points. Something that actually at the moment sees a large political pressure to actually strengthen the grid, especially from sites where we produce all the wind power, for example, in the North Sea region, to transport it south to at least Bavaria and use it up there. There's a couple of lines actually needed to get all the power down south And then the solar energy the other way around, from the south to the north. So yeah, I think you're all aware of this, right? There's nobody that I really need to explain this. In Europe, in the European grid, the set point is the 50 hertz, and if load and generation are in balance, we have the 50 hertz, and we don't ever see that it is just 50, but it needs to be balanced out. And it's balanced out by as it is in the rest of the world as well, a three-step system there. Sorry, I took this slide reflecting on tertiary reserve capacity. That's why it's mentioned in above, but I just want to hint at the situation here that we have, that overall in Europe, if we see a frequency deviation, primary reserve capacity in the large generation sites actually hits in and tries to reestablish the set point of the frequency. And it's a burden sharing, right? We see a deviation in the frequency in the European grid, and all the big power plants kick in. And then after at least 30 seconds, they're freed again, and secondary reserve capacity power plants are started. Secondary reserve capacity can be like very quick gas-fired power plants, or it could be water storage power plants, as we have that here in Hamburg, in Geesthacht. So whenever there's more electricity in the grid, water is pumped uphill, and it's done in the secondary reserve capacity, so as a reaction on the frequency actually. And whenever there's not enough electricity, so the frequency is below 50 hertz, then they let the water run down the hill and have it on turbines produce electricity. Now secondary reserve capacity is substituted by tertiary reserve capacity, or at least aided by tertiary reserve capacity, and that is slower systems that actually need a couple of minutes to get started. And anything that's, well, any deviation that we see that is longer than an hour is called hourly reserve, which is not really a reserve, but a re-establishment of actual scheduling of generation and consumption sites, right? So, what have we done in the E-Island project? E-Island was a project that is, or ran through March 2010. We had only a very limited funding, since research at University of Applied Sciences is not that strong in Germany. You're supposed to actually be more teaching than researching. So the universities get quite a bit of funding for research projects. Universities of Applied Sciences have to struggle for funding, which gets better when you deliver results, which is a situation that I happily foresee or see at the moment with my research group there. So we cooperated in this project with the city of Hamburg and Evonik Industries, which was probably the breakthrough, because they said, if you are finding a lot of capacity, we are going to integrate it in our project, or in our concept. They have a virtual power plant running that is just delivering tertiary reserve capacity. So what they do is they cluster all kinds of sites in Germany that are able to produce tertiary reserve capacity and put it on the tertiary reserve capacity market. That could be CHPs, it could be emergency diesel generators, but it could be as well, and that was what we researched, sites that are able to use a bit more flexibility in electricity uptake that they have in the demand, actually. And two German engineering companies that we cooperated with, the Nvidia that supplied us with hard stuff, hardware, and Zombie Engineering, an engineering company that I founded, doing some concept work. Right, that's what it actually looked like in the end. We did a model. It was all about modeling. We got 250,000 euros, so there was nothing that we could actually really build and run, rather than having smart meters set in different sites at the city of Hamburg to actually measure high-resolution electricity demand. And what we got is a model of a situation where all the large sites in Hamburg that are public sites, so that are run by the city of Hamburg and that are connected to the medium voltage level, no low voltage level connection, but medium voltage level, as is this campus of the university, for instance. We modeled that all these would have demand-side management facilities. Yeah.
Are you using standalone software or system to monitor this, or you developed your own system? Yeah.
No, we used off-the-shelf techniques for that. So smart meters, well, yeah, smart meters that were actually purchasable, that NVIDIA, the company NVIDIA, would use for energy monitoring in industrial sites. And I said, okay, use this. So we set them up, and they ran a server for us where they collected the data and supplied us with the data. So all the data collecting and well, serving was done by them. And that's basically the only thing that we really put into reality, right? The servers are still there, so one of the server is still there, and the meters are still there. So one of the meters is ticking in the cellar of this complex here. And actually, you would find the HAW campus Bergedorf ranking 4th in the amount of electricity consumed every year by public properties at medium voltage level. First is the Central University of Hamburg, the central campus. And after that, the University of Applied Sciences' campus in Berliner Tor. So the universities are the largest energy consumers, actually. They are consuming, they're taking up more electricity than the central market, where fruit and vegetables are traded every morning. Public properties, right? Not talking about private, industrial, anything, but only the public sector. Okay, then we have all kind of other interesting load shapes that we found. Here, for example, is a sediment dredger. Funny thing that they need to dig out the sludge from the harbor, right, to ensure that the harbor is still reachable by the large ships, because lots of sediments actually wash in with the tide. So they have to dig that out, and they bring it to a treatment plant. And when they come with those boats where the sludge is in, they put in an over-dimensioned hoover, actually, that sucks out the sludge from those boats. And whenever there is a boat, they put on that hoover that actually sucks it out, and it takes up 1.5 or 2 megawatts, actually, and only runs for 15 minutes, and then the boat is empty and gets off again, getting new stuff. So that's kind of an interesting load curve there. Right, so what did we do? We simulated what the situation would be like if all those sites had load management facilities. Now, load management facilities, again, is something that you can buy off the shelf. It's just something that prevents a single site, a single property, from having a single load curve. And that actually is what we came to that problem from, because the city of Hamburg was running a program to reduce the load peaks in the public properties, because that was expensive. And then we had the situation of, the unbundling in the electricity market, leading to lower prices and leading to lower prices in the power. So the peak power was not that expensive anymore. And the city was asking itself, now what do we do with our nice load management facilities that we put up in the public properties? And then we came up with the idea, do a network. Interconnect them. It's all computers, actually, so you could connect them via the internet. And what could be the result? That basically was the main research question. So we simulated an internet-based network of load management devices in the 20 biggest public properties of Hamburg. Now, big just means lots of electricity, 20 most important electricity consumers. Those were the results. What we found is that for the two options, one would be smart balancing, and I'm coming to that in a minute, and the second would be providing reserve capacity. We found that, first of all, what you get is quite a predictable system. Rather than just doing a prediction for your load uptake tomorrow and then doing a blind flight through it, you could now monitor your sites and directly look at them and notice when you have a deviation from your schedule. And then, not only that, you could rule out that deviation. You have your prognosis, you have your meter reading, it's minutely meter readings, and then you see a deviation coming, and you can rule it out. And what we could do is, we could rule out 98% of all scheduled quarterly hours within a 5% tolerance range. That would be the same for a 4% tolerance range. 3% is then getting too narrow and system starts swinging. But that was quite good, especially because the prediction software that we have was self-made. So it was not a professional one. Predictions sometimes were pretty lousy. Most of them were quite good, but sometimes they were not so good. And then we had a look at the reserve capacity, and then we figured that we could deliver to the market 2.5 megawatt reserve capacity during peak hours and about 1 megawatt during off-peak hours at night. Negative, that's positive reserve capacity. So positive reserve capacity in terms of consumption would mean lower the consumption. Because that has the same effect in the net. You lower the consumption, it's just the same than raising the production. Same effect. Now, negative reserve capacity, that would be something that would be needed when you have too much electricity consumption, say, coming from wind. And we asked the system, what can you take up? And we found it can take up quite a bit, 5 megawatts. But that's with a big but. And the but is we have one very large consumer here, the motorway tunnel under the Elbe, that has a lot of ventilation capacity. And that's emergency ventilation, right? When they have a fire, they need to suck out the smoke. Now, if you could use the without the emergency ventilation, still use all the ventilation that they have installed regularly, and then that would range up to 5 megawatts, or basically 3.5. And the rest, the 1.5, would come from the central market, where there's lots of cold storage actually running that you could use to actually take up more energy, produce more coal, and then later on you don't have to produce the coal, right? So that's okay, this one, because it's really energy storage. You take up more electricity, and then in a couple of hours you don't need to take it up. But this is just, you can't destroy energy, but it's a bit of a waste, right? You switch something on that is not really needed, rather than doing something sensible with it. So we found that this is not nice, but the system would be able to do it. And the Evonik people actually were quite fond of it. They said that this is what we're looking for. We're looking for large size. There's only one customer, and it's delivering quite a bit of power. So that's interesting, right? It wasn't so interesting for us, and it wasn't so interesting for the city of Hamburg. So this is why we had the follow-up research project and said that's probably not the best electricity storage you could find. There must be better sites in the infrastructure of a city that are able to take up electricity and really do something sensible with it in times when there's too much electricity in the grid. So, but again, for the results, the first thing, the smart balancing, was interesting to see because what you could do with a system like that is go for a direct electricity purchase rather than have a wholesale contract for the city of Hamburg. The city of Hamburg has a wholesale contract for all its sites. All the sites can join in. They don't have to, but they can. And since it's a cluster of sites, they get a really good price. But still, it's a wholesale contract. That means all the risk is counted in the contract. So all the deviations that the supplier really has when he does his schedule for the next day and buys the electricity is already calculated in. We said, okay, if we can reduce that risk and then buy the electricity ourselves at the electricity exchange, that might save us some money. And we found out, yes, it does. But it's a bit unpredictable. In 2007, we found it would save the city 3 million euros. That's quite a bit. But the next year, it was nothing. It was virtually nothing. It was a couple of €100, so it doesn't really count. And that was because the wholesale contract was so good and stock exchange prices in that year were so high that there was no effect. Actually, I was talking to suppliers about this, and they asked me, what's the price that you have in the wholesale contract? And I told them the price, and they said, oh, that's great. Can we buy the electricity from you? So they really have a good price. It's quite a bit strange. But still, there's a couple of hours that, you know that are really expensive. It's the peak load hour contracts in the midday, right? Those tiny hours here, they are expensive. If you could avoid having to buy those expensive contracts at the exchange and produce it yourself with CHP, say, right? You could still, in a year like that, save a lot of money. 1.5 million euros we found out that could have been for 2008 if it was only avoiding a couple of hours with a limited capacity. Because this virtually doesn't cost you anything. It's not really for free, but it's very, very cheap, right? And then it's getting more and more expensive the more you get to the peak load hours. So this might be an interesting concept, and we're still working on it with in one of our follow-up projects. Okay, and the other thing I told you was the situation with the tertiary. Yeah, there's a question. No, no. They have the same conditions in their contracts, so the price is the same for everybody, but every site is billed individually. But it's just that in the end, you can sum it up, and then you have a total price that it costs the city, right? Because the city covers for the costs.
So it's something like a common agreement for the negotiation,
Yeah.
but then afterwards they pay each other their own bill.
Right. It's basically just a bulk contract, right? And you say, oh, we come up together, and then the amount is higher, and we get a better price. Which is a great thing to do, actually. I do a lot of consulting with industrial sites and stuff, and only the large industrial sites get prices that get similar or better to what the city of Hamburg gets because of this bulk purchase. Quite a bit. Okay, yeah, here's a curve that actually just tells you what we did. We did a prognosis of the load uptake, a load schedule day ahead. So we play the game saying we just know up until today, and then we do a prediction for tomorrow, knowing the data for tomorrow already, right? And then the blue is what we predicted, and red is what we really got on that day. And you see it's pretty close. The purple there and the green there is the 5% margins around what we predicted. So we just had basically a two-way controller, right? And here's a deviation that gets into the range of the allowed deviation there, here, over there, here in the end. Now in the simulation, that could be ruled out by the controller, just with the capacity in the buildings. Things that we would switch would be, say, the ventilation system or the climate, the air conditioning system. It could be large cooking facilities in the central kitchens, like that, what we have in the Mensa over there. Things like that. So only things that the actual users of the buildings would not notice that they are switched. So switching for a ventilation system would, say, last 5 minutes, switch off for 5 minutes, and then it runs again for the next 10 minutes. And well, we'll leave it at that. I was starting to talk about frequency control ventilation and what we do then, but you can ask me after that. Right, so we could rule it out. So the yellow was what we would have seen if we wouldn't have done anything, and the pink is what we actually got after the regulator set in, right? And the line here in the middle is what we wanted to have. So the situation was get the yellow back onto here in the middle. And it worked out pretty well, actually. As I said, 98% of the quarter hourly loads could be met. Now this is an example for a reserve capacity delivery, starting here. And then we said, okay, if we want to make sure to deliver the right amount of energy, the upper limit should be the amount or the distance between the old schedule and then the upper allowed limit should reflect the amount of energy that was delivered by the system. What you can see here is that if we go to the limit, we have a lot of load noise, and that is due to the in the load management system installed controller algorithms. They react together, and if you have lots of them together and parallel, they switch parallelly, and that gets you a lot of load noise. So this is definitely something that you would have to optimize if you want to have that system on a large scale. You need other algorithms than the ones that are in the off-the-shelf technique, right? And you get those jumps back to the impulse. When the impulse gets back to the old schedule, you get here an answer that looks like that, something that you would have to rule out. But still, it works. So we could show that on a normal day, we can deliver about 2.5, and this is positive reserve capacity, and about 1 megawatt in off-peak hours. This is if we switch everything off all the time. This is if we switch everything on all the time. And now, coming back to the original problem that we have, or that we are going to have in 10 years' time, that's quite a short time frame, actually. What we have at the moment is a system that takes for granted the yellow, and it just reacts on the yellow. What we do is we follow the load, right? Production follows the load. But that's not set. We could do this instead, or we can do that instead. I mean, this is not nice because of the load noise, but still, it's quite a bit lower, and it can be quite a bit lower for quite a long time. Or it can be quite a bit higher for quite a long time. The yellow is not set. It's flexible. You just have to make it flexible. And that is actually what we have a deeper look at in the follow-up projects now. Follow-up projects. One follow-up project is so secret, I'm not allowed to talk about it, but I'll still hint at it. One of the large electricity suppliers has come up to us and said, after they've seen the results, could you do some control algorithms for 100,000 heat pumps? Because what we see in the moment in the home sector is that the heating system is switching to heat pumps rather than having gas-fired fireplaces, heaters. And they say, okay, in the future, we want to be able to actually interconnect all the heat pumps and then have them run when there's lots of electricity in the system, and then not have them run, please, when it's gas. Control it. And then they figured we still have quite a bit of electric storage heating in the system at the moment. Capacity in this might be quite big. Could you do some algorithms for that so that we can control that as well? And then in the future, we will see a lot of e-mobility. Well, and if you're already working, could you integrate e-mobility as well? Last point, we neglect that a bit, but that's something that we're working on, or have been working on for the last year, and probably, so we came to a nice end with some nice results. Probably will be working on in the next step in the next year. But then the next public-funded project that I'm allowed to talk about is e-Harbors, which is a European project, an indirect project. And indirect projects are not so much research projects, but rather regional development projects. And this one, e-Harbors, or e-Harbors is a project in the North Sea indirect frame. So it's covering cities that are located in the North Sea region. Right. What we do, we run a couple of showcases to actually show what the potential of virtual power plants, smart grids, could be in harbor cities, actually. And there's a couple of partners involved, Zaandam near Amsterdam, actually, Antwerp, Malmö in Sweden. So these are Dutch cities. This is Belgium, Sweden, another Swedish, Dundee and Aberdeen, Scotch, and us over here in Hamburg. Time frame is up until 2013. And the University of Applied Sciences has a budget of €500,000. And what we're doing is basically what we've done in the E-Island project, only that we now reflect on the installments in the harbor. So we have a look at the harbor infrastructure and ask the question, what of that would actually be more flexible? if you would apply the intelligent solutions that are needed to make it flexible, actually. And we found that quite a bit is in cold storage facilities, where actually lots of frozen goods are stored for a period before they're transported again. And you don't have to actually have the compressor running that is producing the cold when the thermostat in the room says, now you could switch on. But what you could actually do is, well, give the thermostat the overall control, but then play with the capacity of the temperature storage that you see there and use it to take up electricity in times when there's lots and not take it up when it's short, right? Okay, and there's other things that could be used. So one interesting, for example, is the harbor, the Port Authority runs a railway system, and in winter they have heaters for the railway switches so that they don't freeze. It's 5 megawatt capacity, and it's only triggered by a thermostat. And it's all triggered at once. So they switch it on, it's 5 megawatts. They switch it off, it's 5 megawatts less. Not really sensible to do it that way. Lots of pumps that actually do the dewatering of the hinterland. So they pump the water, the rainwater above the dikes into the River Elbe. They're just constantly running, or they're triggered by swimmers actually that control the level of the water in the collection basin. But that could be used as well. So there's quite a bit of electricity consumption that does not need to run at that time that we have it run at the moment, apart from having too much installments running anyway, right? Whenever we investigated a site, we found that there's quite a bit to do in terms of energy efficiency. Okay, e-harbors, just looking at the harbor there and finding demand-side integration potential in the harbor. And then we have, this is probably the biggest project and quite interesting as well. Of course, it's not only simulating something, but really building it. This is a project that's running up until 2014 there, together with Hamburg Energy, a new energy supplier that the city of Hamburg put up, actually. After they sold their old electricity supplier, they found that it's nicer to have one that you could actually politically control, so they founded a new one. This is Hamburg Energy there. And with them, and together with the University of Aachen, the Technical University of Aachen, we are going to build a virtual power plant. Then that's going to be put on 2 pillars. One is the realization of the e-island demand-side integration approach. We're just looking for sites that we can actually really integrate and do load management with. And the second then is CHP with partially electrically controlled production. Question is the electricity demand of who is actually then going to be covered by the CHP. Because the interesting thing is that if we do a schedule for a lot of sites and then monitor those sites and then we see a deviation and say we're short, we don't have enough electricity, could be that the overall system is large at this. So our deviation is not really a problem. But if I only look at my schedule and my deviation without looking at the system, then I might rule out this deviation just because I intend to rule out all my deviations. It might be wrong. At the moment, actually, with my deviation, I'm earning money because the electricity system itself is large, and I get it basically for free. So it's important to actually look at the system, at least at the net frequency, to find out, shall I rule out my deviation or shall I not? And we need business models for that actually integrate this concept. Apart from that, we are trying to put it up as an open platform concept via standardization so that actually any CHP owner could say, okay, I'd like to connect my CHP onto your platform. And then we can say, okay, it's standardized via the ISO 61850, and this is the module connected to your CHP, and then you can take part on that platform. It's going to be very exciting to see how far we get, actually. So the aims are quite high, and I'm not sure what we can really establish, but well, we'll see. The last year, 2014, is going to be an evaluation year, planned as an evaluation year, so only to test the system and see what do we really have installed, what can we realize as concepts and stuff. Okay. So with this, I'm coming to the conclusions. First conclusion is, we don't need new baseload power plants, at least in Germany or Europe-wide. And actually, we're building one of the last that we will see in Germany, here in Hamburg. One very, very large coal-fired power plant. But the large electricity providers, they know that time for those probably is over. What we need instead is quick, flexible, predictable, and controllable generation systems. That could be CHP or gas-fired generators. And what we need is virtual power plants. So connected smaller units in virtual power plants, supporting the renewables in the Energiewende. What we require is greater flexibility, and that's important, in the uptake of electricity. More demand-side integration. Buildings that have been just electricity consumers get a new role, because they're both. They could be a site that is consuming electricity more flexible, or they could be a site where you have a generator running, a CHP, say. So they get prosumers rather than be consumers. Here at the Center for Demand-Side Integration at the HAW CC4E, we are trying to develop our solutions for, well, both these concepts. Thank you.